Hello everyone, this is Zhihe Lu. Today, I'm going to present our work Beyond Soul Strengths, Customized Ensembles for Generalized Vision Language Models. Currently there are so many powerful foundation models. How to leverage ensemble learning to leverage multiple foundation models to work together for improved performance is a timely research. So we are the first to focus on vision language models. That is how to leverage ensemble learning for generalized vision language models, especially the model we focused here is CLIP model. So first I'll give some background. So for CLIP model, so in this work, they collect 400 million image and text pairs and also use two encoders during training. So these two encoders are used to embed different modalities. So that is, so the image and the text will be embedded by different encoders, and after embedding, these textual feature or image features will be used to do the alignment. So how to do that? They do it in a contrastive way. So that is, the objective is to force the paired image and the text to be close to each other, and force the unpaired image and the text to be away from each other. So after training, this model actually can classify some images given solely the class names. So this is how the CLIP model works in zero-shot manner. So that is during real life. When you want to classify one particular class, you just need its name. So here, for example, in this figure is cat. So you just we can combine the template, a photo of a with the class, and then we input it into the text encoder and we get the text embedding. This embedding can be used to compute the similarity with the image feature. So if the similarity is high enough, that means this image actually belongs to that particular class. So behind is actually the formulation to compute the similarity and the final prediction. So actually for CLIP model, there are multiple vision encoders and language encoders. So especially for vision encoders, they adopt different architectures. Here we show that actually with different vision encoders, the performance are hugely different on different data size. So here, as we want to actually apply the ensemble learning for generalized vision language models, so here we mainly focus on four CLIP models, namely ResNet 50, ResNet 11, YTB32, and YTB16. So we leverage these four models to do the ensemble learning. So especially we focus on different scenarios. Specifically, there are three practical scenarios. So as I illustrate here, so we have three conditions here. So one is the CLIP models. Second one is the small data set. Third one is the training resources. So in the first setup, we consider that there are only the pre-trained CLIP models. So how to do ensemble learning in such a scenario? So in the second step, we have both the pre-trained CLIP models and an extra future data set, but we cannot train the model. So how to only leverage the inference to do the ensemble learning? So in the setup 3, we consider all of the conditions. That is, we have the model, have the data, and have the training resources. So how to design a useful or effective ensemble learning strategies in such a setup. So first, let's come to the first setup. So given solely pre-trained clip models, actually in such a scenario, we propose the zero-shot ensemble. Actually, we can leverage the confidence from the logic. Actually, as we have n clip models, so we have logics from each model with the input, right? And then this logics, in each logic, we have different values on different classes. So we extract the highest property value from each logic, and we consider this as the confidence for that particular model on that input image. So this value will be used to do the softmax, and then we can get the normalized value. So this value can be regarded as the weight for each logic, and then we can use this value to weight the different logic to get the final one. Especially we found that if we already know the best performing model, for example in our scenario is the clip VITB16, and with this model actually we can assign a higher weight. For example, here is 1.0 to the highest performing model, and then for the other models we can leverage our confidence aware weighting. So in this way the performance can be further improved. And in the second setup, we have the pre-trained clip models and an extra few shot dataset, but we cannot train the model. So we can only leverage the inference. In such a scenario, we propose the training free ensemble. Especially our method is actually based on the greedy search. So as we have a few shot dataset, we can do inference on that dataset, and then with this inference we can search some weights for each model. So for example, if we have n models, and we can assign n weights for each model. Actually we can do it on logics level. So we can assign different weights to different logics, and then we can get a accuracy value on the few shots dataset, right? And then we can repeat this process and find the optimal weights on this particular dataset, and then this actually we assume these weights are actually the optimal weights for the few shot dataset, and it also generalizable to a new dataset. And in the third setup, so given pre-trained clip models and an extra few shot dataset with training, actually we propose the tuning ensemble. Especially in this work, on this method, we propose the sample aware weight generator. So the input for this sample aware weight generator is the image features. We first extract n features from n pre-trained models, and then this feature will be concatenated together as the input for the sample aware weight generator, and then we can generate the weights for each model. So different from the previous strategies, here our method is actually sample aware. That means for each sample, we can have a specific set of weights for different models. So this is more dynamic and adaptive. So that's some performance with our ensemble strategies in different data size. So first is the zero-shot generalization and ablation study. We can see that in the left table. So with the ensemble strategy, so the performance can always be improved, especially there is a huge performance gap between the highest performing model and our model. Actually, from the averaged accuracy, we can see our ensemble learning can actually surpass the best single model by 2.61. So it's a lot. So in the right table, we show the evidence study with when increasingly add models, the performance can be improved gradually. And this is the base to new generalization. So that in this setup, we train the model on some base classes and then test the model on normal classes. Actually, these base and null classes, they are non-overlapped, so it is more challenging. But we can see with the ensemble learning, the performance, we achieve a new state-of-art performance, which always surpasses the previous method by large margins. And also, we do not incur a lot of inference delay. So it's compared with the performance improvement, it is reasonable. And the next is the cross dataset evaluation. That means we train the model on the internet and then use the trained model to test on the other datasets. So we can see our method can achieve a much better result. And this is the domain generalization. So we actually leverage ImageNet and its variants for this environment and for this experiments. And actually we train the model on ImageNet and then test it on different variant like ImageNet V2, ImageNet Sketch, ImageNet Art, and ImageNet Real. So we can see the performance. Our method can achieve new sought-out performance. Okay, finally, let me summarize our work. So in this work, we propose a comprehensive study for ensemble learning of vision language models, especially the CLIP model, which is one of the most popular vision language models. Secondly, we consider 3 practical scenarios and proposed 3 tailored ensemble strategies to boost the performance of multiple models. So third, we evaluate our method on diverse tasks and data sets to show its effectiveness. Okay, finally, this is my contact information. That's my email and the code link. So you're welcome to discuss with me for some further details. Thank you.